Hello, and welcome back to our Chemistry Masterclass. Today, we are unlocking one of the absolutely most important skills in all of science, the language of chemistry.
Script written next to an atom, just assume it's a 1.
Section 1. The chemist's code and meeting the ions.
Before we write sentences, we need to meet the main character. To fix this, scientists developed a brilliant solution called the stock system. To achieve perfect clarity, we literally write the metal's charge as a Roman numeral in parentheses right in the middle of its name. If we have FeCl2, the iron has a +2 charge, so we name it iron 2 chloride. If we have FeCl3, it becomes iron 3 chloride. In our sample problem, chromium with a +3 charge bonding with fluorine gives us chromium, parentheses, Roman numeral 3, close parentheses, fluoride. So always check your transition metal charges before writing the final name.
Section 4.
As we continue to decode the fascinating world around us.
Hello, and welcome back to our Chemistry Masterclass. Today, we are unlocking one of the absolutely most important skills in all of science, the language of chemistry. You know, just like learning a new spoken language, chemistry has its own strict set of rules for writing formulas and naming compounds. So if you've ever felt completely confused by terms like sodium chloride versus carbon dioxide, don't worry, we've got you covered. By the end of this comprehensive explainer, you're going to be able to look at any chemical formula and name it instantly, or even turn a name into a perfect formula. Let's break these rules down step by step.
Here is our straightforward roadmap for today. 1. The chemist's code. 2. Binary ionic compounds. 3. The transition metal trick. 4. Covalent compounds and prefixes. And 5. Summary and master practice. Let's get right into it. Let's set the stakes here for a second. Have you ever wondered how we magically make sense of the microscopic world using just a simple, universal set of written rules? I mean, think about it. Atoms are way too small to actually see, yet chemists all over the globe, no matter what their native spoken language is, can communicate incredibly complex molecular structures to one another seamlessly. And they pull this off by using a highly structured chemical alphabet and grammar.
To fluently read this language, you first have to understand its basic words. A chemical formula simply indicates the exact number of each kind of atom in a chemical compound. You can think of chemical formulas as words built straight from the alphabet of elements on the periodic table. Those tiny little subscript numbers, they act almost like pluralization to tell us exactly how many atoms we have. So, for example, if we look at octane, which is C8H18, that tells us there are exactly 8 carbon atoms and 18 hydrogen atoms. And a quick pro tip, when there's no subscript written next to an atom, just assume it's a 1.
Section 1. The chemist's code and meeting the ions.
Before we write sentences, we need to meet the main characters of our chemical story, the ions. Elements rarely just sit around by themselves. They love to interact. We define our 2 distinct types of ions based entirely on whether they give away or collect electrons. If an atom loses negative electrons, it becomes a positively charged cation. If it gains extra negative electrons, it becomes a negatively charged anion. To remember the difference, just picture a happy, positive little cat for cations, while anions pick up extra negative baggage. And why do they do this? To reach a magical, highly stable ultimate goal called the octet, that perfect outer shell of 8 electrons. Because they're perfect opposites, positive cations and negative anions are fiercely attracted to one another.
Section 2. Binary ionic compounds. Let's look at our first major category.
These compounds form when a metal bonds with a nonmetal by physically transferring those electrons. To translate these interactions into written formulas, we use a sweet and simple mathematical grammar known as the Criss-Cross method. Here's how it works. Step 1. Write the symbols and their charges, always putting the positive cation first. Step 2. Take the numerical charge of the positive ion and cross it over to make it the subscript of the negative ion, and vice versa. Step 3. Simply reduce those subscripts to the lowest whole number and drop any ones.
Check out this elegant switcheroo in action with aluminum and oxygen. We want to combine aluminum, which has a 3 positive charge, with oxygen, which has a 2 negative charge. The 3 from aluminum crosses down to tell us we need 3 oxygens. The 2 from oxygen crosses down to tell us we need 2 aluminums. The result? The perfectly balanced formula, Al2O3.
So, how do we speak this code out loud? It's honestly a breeze. You name the metal first, exactly as it is on the periodic table. Then, name the nonmetal, but give it a cute little makeover by changing its ending to an "-ide" suffix. So sodium and chlorine become sodium chloride. Magnesium and oxygen become magnesium oxide. Super easy, right?
Section 3, the transition metal trick. Let's see how this builds into a special grammatical twist.
For the middle block of the periodic table, things get a little tricky. Transition metals are basically chemical chameleons. They can form ions with entirely different charges. For instance, iron can casually have a +2 charge or a +3 charge depending on the situation. Without a strict rule, this would cause massive confusion. I mean, if we just said iron chloride, a chemist wouldn't know which version of iron we were talking about. To fix this, scientists developed a brilliant solution called the Stock system. To achieve perfect clarity, we literally write the metal's charge as a Roman numeral in parentheses right in the middle of its name. If we have FeCl2, the iron has a +2 charge, so we name it iron 2 chloride. If we have FeCl3, it becomes iron 3 chloride. In our sample problem, chromium with a +3 charge bonding with fluorine gives us chromium, parentheses, Roman numeral 3, close parentheses, fluoride. So always check your transition metal charges before writing the final name.
Section 4, covalent compounds and prefixes.
Next, we're going to throw out the Criss-Cross rulebook entirely as we enter the world of covalent compounds. These form when two nonmetals share electrons rather than trading them. The naming rules here are completely different because we don't need to look at balancing charges anymore. Instead, we rely on the old Greek prefix system attached directly to the elements to tell us exactly how many atoms of each are present in the molecule.
These prefixes act as our direct counting mechanism. Mono means 1, di is 2, tri is 3, tetra is 4, penta is 5, and hexa is 6. You simply state the prefix, then the element name.
Let's look at some famous examples to see this in action. If we have P4O10, we literally just read the numbers using the prefixes, tetraphosphorus decoxide. But for our second example, CO, we run into the one golden rule of this entire system. CO has 1 carbon and 1 oxygen. It becomes carbon monoxide. Notice something? We never use the prefix mono for the very first element in the compound. We just say carbon monoxide, absolutely never monocarbon monoxide. Likewise, CO2 is simply carbon dioxide.
Section 5, summary and master practice. What an incredible session, unlocking this vital scientific language.
Today, we mastered the foundational laws of chemical nomenclature. The crucial takeaway here is this simple step-by-step checklist. First, identify your compound type. Is it a metal and a nonmetal? Then it's ionic. 2 nonmetals, it's covalent. Second, pick the right grammatical rule. Use the Criss-Cross method for ionic charges and apply Roman numerals for those chameleon transition metals. Third, if it's a covalent molecule, forget the charges entirely and just use Greek prefixes to count the atoms. Mastering this checklist is literally your passport to success in translating the microscopic world.
To leave you empowered today, I have a challenge for you. It's time to practice your new fluency by reverse engineering a name back into a formula. Grab a pen and piece of paper right now. If I give you the name magnesium iodide, what is the hidden chemical code? You'll need to find magnesium's charge, find iodine's charge, and cross them over. I'm going to leave you to ponder that one. Make sure to keep testing yourself with new compounds, and I will see you in our next explainer as we continue to decode the fascinating world around us.